Okay, welcome back. So we're moving on to section 7.5, which I'm calling higher order linear Cauchy Euler type ODEs. So basically the last section, you'll recall it was saying in higher order problems we have to get restrictive on the sorts of coefficients we can place on the dependent variable or the function we're trying to solve the ODE for in one dimension. We have to get restrictive on this coefficient. And Cauchy Euler type is a new version of restriction on those coefficients. So we're allowed to go a little bit broader than constant coefficients, but this is very restrictive still. So we have this whole idea of a constant coefficient of a sub j, but we're allowing ourselves powers of t. But the important thing is that the power of t has to agree with the derivative in y. So that's what I'll say. The power on t, which could also be or on x, etc., whatever our independent variable is, the power there needs to agree with the number of derivatives. And, that's not perfectly true, because I could multiply or divide both sides by some monomial of t and shift maybe the powers of t over to the right-hand side. But I definitely need this whole idea of like stepping up by powers of 1 as my orders of derivatives get higher and higher. So I'll give a nice example of this. For example, if I have something like t squared y double prime plus ty prime plus 2y, you can see there's really, maybe I'll say this is equal to cosine t. There's really like a zero power of t sitting right there, a first power of t sitting right there, and a second power of t sitting there. Or something like even t to the fifth y 1 2 3 4 minus 2 t to the fourth y 1 2 3 plus t cubed y 1 2 plus 1 2 t squared y prime minus t y equals 0. This doesn't exactly look like it's Cauchy Euler type because I have a 4 derivatives and then a 5 on t, a 3 derivatives, 4 on t, and so on. But you'll notice that if I divided everything by t, then I would get that property. And so really, I guess this needs to be satisfied up to manipulations of the entire ODE. We can always try to simplify things before we try to solve them. And if the ODE, that's why I guess I should say, can be written as this ODE, not that it will necessarily be presented to you as this ODE. Those are two different things, right? But we can still recognize that as the order of the derivative gets higher here, the order of t exactly steps up, right? So y to the fourth, t to the fifth, y cubed, t to the fourth, and so on. And this is the derivative known as Cauchy Euler type. Some people will just call this Euler type, I believe. But I've seen it as Cauchy Euler type slightly more often. So we're going to work with Cauchy Euler for a little while. I have to introduce the following definition, and it's a little bit tricky to think about what's actually going on here. But we need it to solve these problems, okay? So this definition is called the falling factorial. And why is it use the term factorial? Well, just like a factorial would be something like, okay, so n factorial is like, jump back a little bit. It's like n times n minus 1 times n minus 2 dot dot dot. The falling factorial is very similar, right? So I'm taking lambda, falling factorial j times. I'm starting with lambda, then multiplying by lambda minus 1, multiplying by lambda minus 2, multiplying by lambda minus 3, and so on. But the thing about the falling factorial is that it stops after j total terms. J total being if I start at 0 after j terms, I've only made my way to j minus 1 as a subtraction. So that's why we call it the falling factorial, and we notate it really interestingly as lambda, if I'm using lambda as my variable here, lambda to the underlying j. So you use it like lambda to the j because it is a jth order polynomial, right? I have j, or jth degree polynomial. I have j total lambdas there, so this will be a jth degree polynomial. And it's not quite a monomial because I do have non-zero lower degree terms, but in some ways it behaves similar to a monomial. And we'll see why in a bit. So we use this terminology that looks similar to monomial terminology, but we're using an underline in the power. And there are just two different ways of thinking about it. You can just take lambda and multiply by lambda and then lambda minus 1, lambda minus 2, all the way down to j minus 1. Or you can think about it in product form, which is not that difficult to write out because it's just a product, lambda minus k. And of course, if I'm doing each of these, then that's the product that I get out of it. I can also, if anyone's familiar with the gamma function, right, because the gamma function is very closely related to factorials, I can represent this with the gamma function. It'll be gamma lambda plus 1 divided by gamma of lambda minus j plus 1. So you can represent this with the gamma function as well. I put an approximately equal to the factorials here because, what does the top line allow that the bottom line doesn't? This allows for lambda in the entire complex numbers, whereas the bottom line only allows for lambda in the natural numbers. And in fact, in the natural numbers, greater than or equal to j, right? So it's called the falling factorial because under the restriction of lambda to a positive integer and j less than that positive integer, then we can represent this as a ratio of factorials. But for other lambdas, it's not quite so clear that you can do that. And of course, you can't actually do that. But the gamma function is our version of saying, okay, we're just going to define factorials on complex numbers instead, and then everything is perfectly well defined. Except for the couples cases of singularities, because it's technically what we call a meromorphic function. But it has an analytic continuation to all lambda in C. That's what we can say. And you'll get the same idea. So all of these are equivalent formulations of what we call the falling factorial. And the only reason why I'm introducing this is because we have this thing called the indicial polynomial. Okay, this is going to be the equivalent, the Cauchy-Euler equivalent to our characteristic polynomial. Okay, indicial. So given a Cauchy-Euler type ODE, there it is. Remember, it's one that can be written as the following. I'm going to construct my indicial polynomial using a sub j, the coefficients from my ODE. But now instead of just lambda to the j power, I'm using the following factorial for lambda. So this is very, very similar to constant coefficient problems, but I'm modifying my powers of lambda into the falling factorial powers of lambda with Cauchy-Euler type. I don't have to worry about t's. The t's, right, the whole idea with these t's is that they are what's forcing me to head into this falling factorial idea instead of the nicer case that we had before, where we just had powers of lambda. So this is called the indicial polynomial, or like I was saying before with our characteristic equation, once you set it equal to 0, it becomes an equation that we're going to want to find roots of. Okay, so yeah, there's the remark. Notice the similarities between the characteristic and indicial polynomials. Now, this next lemma is just the same as with the characteristic one. By the fundamental theorem of algebra, we can factor this because it will just be an nth degree polynomial. It looks different, right? It's not an nth degree polynomial where the coefficients on each power are given by a sub j. We actually have to compute all of the coefficients by expanding all of the falling factorials. But once we do that, we gain an nth degree polynomial, and that means we can factor it using the fundamental theorem of algebra. And so we go through the exact same process of factoring the fundamental theorem of algebra, and doing that same process, we still recover roots, b sub k, and we still recover multiplicities, alpha sub k. So this feels the same. All we have to do, right, I should say this feels the same as for constant coefficients, but we must expand each falling factorial. So we just have to be aware that the falling factorial is a thing, and we have to expand each of them before we decide to factor our polynomial. Okay, so then the solution comes right from there. The solution will be precisely, instead of exponentials, we have powers of t, and instead of t's, we have logarithms. Okay, so this should feel very similar once again to characteristic polynomial giving the solutions to constant coefficients problems, except now the indicial polynomial will be used, and instead of exponentials and powers of t, we have powers of t to the roots and then logarithms. So we're stepping up in powers of logarithms, and we're taking t to the roots of the indicial polynomial. So I'm not gonna give an example right now because using this indicial polynomial is a little bit complicated. So I'm going to move over into the examples that I've provided for you. Right here, so let's look at this example on the bottom. So this is almost the same sort of idea with our previous constant coefficients version, except now we're stepping up in powers of t. We have y, and then we have 2t y prime, and then we have t squared y double prime. So our indicial polynomial from this, if I want to construct my indicial polynomial, I'm going to take the coefficient in front of t squared y double prime. So the coefficient there is 1. So I'm taking 1 lambda to the 2, but it has the underline saying that that's falling factorial lambda to the 2, right? It's a falling factorial. And then I take my coefficient on y to the first power, which was 2 lambda to the falling factorial of 1. And then my coefficient on y is 1 lambda to the falling factorial of 0. That's my polynomial. My equation is when I set it equal to 0. This is what I need to find roots of. But in its current form, I'm using the underline as a shorthand for, in fact, this polynomial is actually lambda minus 1. This is the falling factorial of 2, right? The second falling factorial. And then I recover plus 2 lambda plus 1, because thankfully these get pretty easy at powers of 1. The falling factorial is very easy, and at powers of 0, the falling factorial is the same as before. It's just the empty factorial, I should say, which is 1. And so that's now what I have at the top here. Lambda minus 1 plus 2 lambda plus 1. This is my indicial equation. And if I find the roots of that, I should expand it out. So I'm going to expand it out to lambda squared minus lambda plus 2 lambda plus 1 equals 0. So the inside terms, I can simplify those to give me lambda squared plus lambda plus 1. And we probably just want to use our quadratic formula to solve this. Lambda equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so that's going to give me negative 1/2 plus or minus I root 3 over 2. So lambda there's two values lambda can take to solve this. They thankfully both have multiplicity 1. And I'm going to give myself a little bit more space here to actually construct my solution using my theorem then. We'll recall our theorem said we take powers of t to the lambda. The solution is powers of t to the lambda, so long as lambda is multiplicity 1. As we step up in multiplicity, then we add powers of log. Okay, so powers of t to the lambda, that gives me y of t is c1 t to the lambda, which was negative 1/2 plus I root 3 over 2. And the second choice for lambda is negative 1/2 minus I root 3 over 2. So there is my solution to the ODE at the bottom. General solution to the homogeneous ODE. So I'm going to scroll down and we'll see that that's actually what we get. Yep, there it is as well. Great. So at the bottom there's the general solution. I think got a little typo here. These are supposed to be negatives. Negative. So there's the general solution to that ODE. Okay, and just like before, I can use the general solution to find the fundamental set of solutions, right, with the correct negative signs that were supposed to be there. I can find my fundamental set by just looking at basically whatever each c is multiplying. And there's my fundamental set. So if I jump all the way back to the beginning of the chapter, actually, so here I am at the beginning of the chapter, and I claimed that the solutions to this very first ODE were t to the minus 1/2, and then cosine root 3 over 2, and sine root 3 over 2, and we have some log t's there. We're gonna talk about where the cosine and sine come from, but now I think you all have a nice hint at to where the minus 1/2 and the minus root 3 over 2 came from with what we've just solved. So you'll notice this is the exact same ODE, and the minus 1/2 and the root 3 over 2 were just in the solution of what we just had. We'll talk about the cosine and sine in the next section of the book. But now you have a little bit of intuition as to where that solution came from. Okay, so jumping back, we can look at the following, right? We can get a little bit trickier again and head up into a much higher order problem. So if I head up into fifth order, we look at the bottom here. Here's a nice fifth order. Fifth order gets Cauchy Euler type because the powers of t exactly agree with the powers of y. And notably, remember, we didn't have to do that right away. But if we can rearrange the equation so that they do, then we have Cauchy Euler type. So this is Cauchy Euler type. And just so we can get a little bit more practice forming the indicial polynomial, let's form our indicial polynomial here, I and d. It's going to be the coefficient, which is 1 lambda to the 5 underline, plus 7 lambda to the 4 underline, plus 11 lambda to the 3 underline plus 2 lambda to the 2 underline plus 1 lambda to the 1 underline minus lambda to the 0 underline. That's our initial polynomial. If we set it equal to 0, that's the initial equation. And we want to expand the following factorials, and then we want to compute the roots. So let's just look at the following factorial that would result from 5 following factorial. So lambda to the 5 following factorial is lambda, lambda minus 1, lambda minus 2, lambda minus 3, lambda minus 4. I can remember when to stop once I get to the total number of terms is the power. Okay, so 1, 2, 3, 4, 5 terms. So that's when I know how to stop with my following factorial. And so that term here would get replaced by actually this product of lambdas. To following factorial to the 4th, I'd get rid of the last term, and I'd have like this product of lambdas and so on, and then I'd have to expand it all out. And this is why computers are very useful, right? Because they'll do it for us. So there I've written it all out for you in its total beauty, and I say it's equal to 0. And if I expand it on a computer, I get the following, right? So I expand everything out and I simplify it, and I actually end up with what's on the bottom here. So everything simplifies relatively well, and I get lambda minus 1 cubed, lambda plus 1, or lambda plus I, lambda minus I. If I decide to follow the theorem using the roots, okay, so I'm going to say roots to solution via theorem gives me the solution y of t. Since I have multiplicity 3, I start with t to the root. T to the root is 1, so t to the first power. C1 t to the first power. Then I step up in powers of log. So I recover log t to the first power, C3 log t squared over 2 t to the first power. This is my multiplicity 3 component of my solution. Okay, so I step up in log t powers. And then my other terms are pretty easy. It's just C4 t to the minus I power plus C5 t to the I power, because those are both multiplicity 1. So there's my general solution, extracted from those roots using my theorem. And I can scroll down and see that that's what I recovered right there as well. And then, as always, we get a fundamental theorem, or a fundamental set of solutions by just looking at each, the function which is multiplying each of the different constants. So the first one is t, then log t should be log t squared over 2 t to the minus I, and t to the I. So those are my 5 linearly independent solutions which form a fundamental set of solutions. And this is how we get it for Cauchy-Euler type. Now I'm going to move on just a little bit. This is all we need to know in practice, but there's a pretty nice proposition here which corresponds to my proposition for constant coefficients, where I said the characteristic polynomial was precisely the characteristic polynomial if I rewrite the equation as a first order equation in like n dimensions. We get the same thing with the initial polynomial, but we have to be a little bit careful. So we don't rewrite it in n dimensions according to the standard one that you've been used to this semester, which was theorem 4.4.1. Actually, we do a different modification. So when we define our n-dimensional variable, which this will evolve in, the n-dimensional equivalent problem that it'll evolve in, actually I define that variable like the following. It becomes t to the 0, y0, t to the first, y1, t squared, y2, and so on. So that's the modification. And then we go through the process of rewriting it. It turns out you can rewrite it in this form. And let's think about what would the solution of something written in this form look like? Well, it's e to the integral log integral, jumping ahead, e to the integral 1 over s ds m, which is e to the log t, this was 0 to, or 1 to t, e to the log t m, which is t to the m. So it's an exponential matrix, but we're doing it in base t instead of base e. And that's actually where we're recovering these t's instead of exponentials in these Cauchy-Euler problems. That's really the entire relationship. Why I get t's there and I get logs here is really, the solution process is very similar, but because of this 1 over t that shows up when we convert it to the first order equation in higher dimension, then we're taking e to the log, and so the e and the log cancel, except for powers of t, which become just log. So that's where those are happening. I'm not going through the full proof because proof, C exercise, you get to do that for me. But that's the idea for why our solutions take the form that they do. Actually, I've got a really nice remark here that I'm not going to talk about because it's a bit of an intense level of math, which is an alternate proof technique of the above. And it deals with this thing called the Stirling numbers of the first kind, which are really useful in combinatorics. So if you've taken a combinatorics course, you've probably run into these curly, it looks like a curly bracket binomial. This is like the equivalent binomial to the falling factorial. You know how the binomial, the binomial coefficients for the regular powers of x, these are the coefficients for the falling factorial powers of x. So we have to write our equations in terms of those if you want to do it that way. So that's just an interesting remark that I would encourage you to read, but if it doesn't get you excited to read it, that's totally fine. You don't need to know it. But that's all we have for this. That's why it's a little bit long of a remark. So that's all we have. Then we'll move on to the next section later. See you in class. Bye.